Alright, so last time we started talking about the static determinacy and indeterminacy a little bit, and then we started solving one determinant structure, and it was a simple frame. So, and I told you if you have problems with drawing bending moment, shear force, moment force diagrams, and getting internal forces and members, there's problems. You have to act immediately. You have to go revise the basics of structure analysis because I can't do two courses here. It's an advanced class, so I'll try as much as you can, to scratch some old stuff, but you have also to do your work in revising the analysis of beams and frames and trusses. Okay, I'm gonna right now solve another example, and this example is gonna be also determinant structure. And if you guys remember what determinant structure is, do you guys remember? We did it last time, just a fresh review. When a structure can be determinant.
The amount of equations is the same as the amount of unknowns.
Excellent. When the number of equations equal to the number of unknowns. And this we call aesthetically, that's how actually the definition, aesthetically determinant. Aesthetically determinant means that you can solve the structure using the static equilibrium. The summation of the forces in the x, summation of the forces of y, summation of the moments equal to 0. That means it's a statically determinant structure that you can solve the structure using the static equation. So the degree of indeterminacy, I believe we called it E, I guess. So when, okay, let's not put it that way. We're gonna do it that way in a little bit. But let's say, can I use this?
Yeah, go ahead.
Thank you so much. All right, so let's say when the number of unknowns is equal to the number of equation, so that's we call determinant structure. All right, and we said that the number of unknowns is more than the number of equation. What is this? Indeterminate structure. Indeterminate that you cannot determine the internal forces or the reaction or solve the structure using the static equation, and we call it aesthetically indeterminate. By the way, it's a determinant using other method, but aesthetically indeterminate that you cannot use the sum fx, sum fy, summation of the moment. You cannot use the static equilibrium to determine the reaction or to solve the structure. But you have to use other methods, energy method, stiffness method, conjugate beam method, and double integration method. So you have to use other method to determine the unknowns. Okay, there is something that we didn't cover, and actually that's a natural question. So we said equal, we said more than, but we forget something. What if it's less than? What if the number of unknowns less than the number of equations?
Unstable.
It's unstable, right? So let's say that you have a structure like this on two rulers. The number of unknowns, I only have two reactions, so the unknowns equal 2. But how many equations do I have? 3. So that means this structure is unstable, right? Why? Because the thing is, if you push this structure that way, it's gonna run. By the way, this structure can be stable in other applications, like mechanical applications, everything is moving. But structure analysis, everything should be static. This structure shouldn't be moving. This desk or the bridge shouldn't be moving. Everything should be stay still. So this is in our structure analysis application. It's not allowed. That's unstable. We cannot design structures like this. All right, so this we call it unstable. Also, this will take us to talk about really, really important applications. Sometimes some structures are tricky. They are the number of equations equal to the number of unknowns, or even the number of unknowns are more than the number of equations, and these structures are unstable. We call them geometrically unstable. Look at this. Let's say that you have a structure like this. Is that stable or unstable? That's stable, right? Yeah. And actually, that's even more than stable. That's stable and indeterminate, right? Because the thing is, this structure can be stable even with a roller. It doesn't need a hinge, right? Let's say that we put a hinge, that we make it more stable, all right? Let's say I'm gonna put an intermediate hinge here. If you calculated the number of unknowns, and the number of equations, they are gonna be equal to each other. Unknowns and equation, 4 and 4. We are gonna see how we calculate the unknowns. You can know them. You have 2 here and you have 2 here. The equations, you have the 3 static equation, summation of x, summation of y, summation of the moment, and this hinge give you an Kistler equation, summation of the moment at this intermediate hinge equal to 0. That's another Kistler equation. We are gonna see how we are gonna calculate this. But if I calculate the unknowns, you are gonna find them 4. If you calculate the equations, they are gonna be 4. So basically, you're gonna say, oh, the number of unknowns equal the number of equations. That's a determinant structure. No, that's not a determinant structure. That's the structure we call it statically unstable. Sorry, geometrically unstable. Why? Imagine with me that you have a structure and a hinge. Hinge means that allows rotation, right? And hinge here that allows rotation. If there's a hinge in the middle, once you put a load in the middle, this whole structure is gonna go collapse like this. It's gonna take something like this. So when you jump on this structure, it's gonna go up and down. We don't allow this. Maybe it's not gonna fail, but it's geometrically unstable. We cannot allow this mechanism in our structures. Okay? So we call this geometric unstable. All right. So how can you distinguish the geometric unstable structures? Usually the structures that have 3 hinges on the same line. If you have 3 hinges on the same line, these hinges can be intermediate hinges, can be bent like this. So if a hinge here and a hinge here are in the same line, so definitely there will be something that's gonna make like this. It can come in different forms. Like this form can be like something, you have a frame fixed here and a frame fixed here. Is this stable?
Yeah.
Yes. And this fixed is stable. Let's say I put a hinge here and a hinge here, and then I made a beam and this beam on a hinge here. That's still 3 hinges on the same line, and this thing is gonna collapse something like this. Sometimes also I have other applications.
So this structure would be
Geometrically unstable. Even it has some pieces that are stable. But since one piece is unstable, so the whole structure is unstable. Sometimes you have a structure like this, and then I put like a frame on top of it, something like this, and let's say I'm gonna put it like this. This one is stable, but let me put it that way.
Isn't there like all those hinges are like those? All those hinges are gonna make
The thing is, if I put it that way, if I put a hinge like this, a hinge like this, and this, that's called 3-hinged frame. That's a stable frame. It's something like this. This frame is stable.
Would that be because of the radio connections?
This one is stable.
But isn't the hinge on top gonna fail? And
No, if
the other
this
one-
thing is a rigid connection and this thing is a rigid connection.
Oh,
Since it's a rigid
that
connection,
is-
it's not gonna fail. It's not like this one. This one, I make it flexible connection, hinge. But this one is like, it's really rigid. It's not gonna allow. Actually, this thing in real life is something like this. Sometimes you will find bridges. In real life, it's gonna be something. And you have a footing like this, and then the other piece of the bridge or the frame is something. Something like this. And there's an illustrated bay that they rest on each other, something like this. So that thing is stable because that thing has a hinge here and has a hinge here. So it's something like you have a hinge and you have a hinge here. So it's a stable. So yeah, I mean, like if I have a structure like this, and it's connected fixed here, but I have 3 hinges here, this is unstable because it's something like this, so that makes the whole thing is geometrically unstable.
Yeah, but for example, in the case of the bridge, it shouldn't supposed to be a roller because of the.
It depends. You can
contraction.
make it roller, and sometimes you cannot. If you want to make a hinge, you can make a hinge. Sometimes, most of the time, it can be. It depends on what you want to have here.
Okay.
Okay. So, and also depends on how's the what do you have here? Do you have like some reinforcement come from here to here that restrain the horizontal movement? Or it is just like an elastomeric band and are just resting on each other? However, if the friction here is high enough to restrain the axial movement, it's gonna be like a hinge.
Okay.
Right? Okay, so there's other maybe applications of, yeah, it's also one good thing. Like if I have something, look at this one. This is a hinge and this is a hinge. All these are on the same line. So once you put a load here, this load is gonna make this frame flip that way and this frame flip that way. And it's gonna make the whole thing geometrically unstable. However, if you calculated them equations and unknowns, you're gonna find that the equation is equal to 4 and the unknowns are equal to 4, and it's gonna give you determinate structure, but it's geometrically unstable. Also, there's another one, something like this, but that's actually easy to catch it. Like if you have a link member, oh actually let's put this fixation. This is fixed. Is that stable or unstable? Stable, okay? So I'm gonna have a link connected to this fixed something. Do you guys know the link member? Have you heard about it? So when you have a structural member that has an intermediate hinge from the top and intermediate hinge from the down, and there is no load in between, we call this member as a link member and only take axial force. It's called link member. But if this member had any loads, like this is not link member anymore. Because right now it's gonna have a bending moment. So if it has a bending moment, that's not a bending, that's like a regular beam. But since it doesn't have any loads in between, and there's the momentary zero and the momentary zero, and there's no load in between them, so the moment is zero on the whole member. Since there's no moment and only axial force, and it's just a link member. Okay? Alright. So this link member is connecting this beam. Alright, what do you think about this one? Is it stable or unstable? This part is stable.
Yeah.
However, this part, let's say that you put a load this way, what's gonna happen? This whole thing is gonna run that way, left and right. So that's unstable. By the way, the very job interview that I had in my whole life, it has a bunch of questions about a structure. The structures that to say are stable or unstable. Okay? So you have to practice, because the stability is number one. Before even solving any structure analysis problem, you have to figure out, is the structure that I'm solving, is it stable or unstable? Sometimes there's a tricky question. I would give you a question, and actually that's how was the question in the interview. Find the reaction and solve for the internal forces for this structure. And my answer was only one word, unstable structure, 2 words, unstable structure, that's it. I didn't put any calculations, anything. That's why when you are very confident in your information, once you look at the structure, oh, this structure is unstable, I'm not gonna touch it. Because the thing is, solving for internal forces, because once the structure is unstable, there is no internal forces are gonna be generated. How? Because once you put a load here, there is nothing is gonna generate it in this structure until it reaches stability. Like let's say I'm pushing this structure that way. When this structure is gonna generate internal forces, when he resists my force. But once he transforms these forces in movement, there's no internal forces. So let's say my structure is here and I'm pushing, it only generates internal forces once it gets locked. And then compression is gonna happen. That's what happens in, same thing here. Let's say I put a load here. There is no load that's gonna be generated until this joint stops moving. Once it stops moving and I put load here, now there's tension is gonna be generated here and tension is gonna be generated here. Okay, we got this? All right, so this is talking about the determinant, indeterminate, and unstable structures. And by the way, there's structures, we call them statically unstable when they satisfy this equation. But these structures, it's called geometrically unstable. They don't satisfy this equation. They might follow this equation, but from the geometric shape, it's unstable, okay? So the first step, when you get a structure analysis problem, decide, is it geometrically unstable? No, so proceed with the equation. If it's not, if it's geometrically unstable, you just write it's geometric unstable. Then once you proceed with the equations and you find that the unknowns equal to the equation, you say it's determinate structure. Unknowns are more than the equations, it's indeterminate structures. Unknown are less than the equations, you can say, before each one of these, you can say it's a statically determinate, statically indeterminate, statically unstable. So right now you should know what is the difference between statically unstable and geometrically unstable. Does anybody have any question? Okay. All right, so with this, I'm gonna solve a problem. Does anybody have any question? Okay. All right, so maybe I will see. Yeah.
Why do you call that an intermediate hinge if it's like basically like at the ends of that link member?
Well, I mean, like we can call it. It's intermediate hinge when it's in the middle, but it's usually a hinge. Okay, so when you have a hinge here and a hinge here, when we make it that circle, because the thing is, when the link member was saying intermediate hinge, because it's like in between two members, it's not like this one. This is like hinge, it's not intermediate, it's a side hinge. So that's why we call it hinge by itself. But once you have it as a circle like this, we always make it this circle when it's in between the structure. So make that circle. And actually, this thing only means one thing, that the moment here is 0, that's it. The moment here at any hinge is 0, allow the rotation. Since the moment here is 0 at the start and at the end, and there's no load in between, so the moment on this member is 0. And only take axial forces, that's why we call it link member. But you have to have this in your mind, if there's any load in between, this is not a link member anymore, that's a regular B. Okay, so now I'm gonna like put the equations, how we can calculate the number of equations and the number of unknowns, because sometimes it's tricky to do it. If the structure is simple, it's easy. Like if I have a beam like this, it's easy. You will tell me, okay, I have unknowns equal 3, equations equal 3, and the degree of indeterminacy equal the unknown minus the equations. So I have 3 minus 3, it's equal to 0. That's as simple as that. However, sometimes the structures are not simple. You might end up with a big structures with a lot of intermediate hinges, with a lot of end conditions, with a lot of members. So we need to know how to do this. However, before I study, like let's put here degree. Okay, degree of static indeterminacy. Alright, so the degree of static indeterminacy, it is this equation. D equal to the unknown minus the equation. That's the general equation. But the thing is, before I dive deep in this, we need to be on the same page on this hinge. We all know that this is an intermediate hinge, right? Do you guys know what this hinge do to the structure? I just said it a few minutes ago.
Yeah, that's it.
Exactly. The moment is what? 0, right? And what does it mean? Like that means like if you take the moment. Okay, let's not start with this. Let's say that this frame is like this. What is the moment here? Is 0? No, right? But once you put intermediate hinge, if you calculate the moment from the left side from the hinge is equal to 0. If you calculate the moment from the right side of the hinge, you're gonna find it's equal to 0. Here, the moment is equal to 0, but if you take all the moment of the whole structure, like if you take the loads from here and the loads from here, they balance each other. Do you guys remember, to make a section stable, the moment from the left should be equal to the moment of the right. If they are not equal to 0, that means that this section is unstable. Okay? So, but if you take the moment from the left, here, it's not gonna equal to 0. There's a number, and this number might be 10. And if you take the moment from the right, it's gonna be equal to 10. Okay? And be equal to each other, and that make this section balanced, and the total moment on this section is equal to 0. That's for any static structure, any structure of these, if they are static, if you take the sum of x at any point for the whole structure, should be equal to 0. The sum of moment equal to 0 for the whole structure. However, this one is a special case. This one, if you take the moment from the left, it's not going to be 10, it's going to be 0. And if you take the moment from the right, it's going to be 0. And if you take the moment for the whole structure, it's going to be 0. Okay? So that's what the intermediate hinge do to the structure. However, this intermediate hinge only provides one equation. You'll tell me, how about one equation? I can take the moment from the left. This is going to give me equation with 2 unknowns. And I'm going to get the moment from the right is going to give me equation with 2 unknowns. That's 2 equations. No. Once you end up putting all the equations together, you are going to find the 2 equations are the same. So like you are going to, it's something like you have x plus 2y equal to 3. And then the second equation is going to be equal to 2x plus 4y equal to 6. At the end, once you put all the equations together, this equation is the same like this equation, it's just multiplied by 2. So it's not going to add any more to your analysis. So usually when you have intermediate hinge like this shape, it only adds one more equation. That's why when we said, here, we said the equation equal to 4, because this one added one more equation on top of the sum of fx, sum of fy, sum of the moment. So it added one more equation. However, we need to have a rule to know how many equations does the intermediate hinge add to the structure. So if you have the intermediate hinge something like this, or something like this, or something like this, so only connect 2 members goes towards this equation, we say that the number of equations equal to 1. That is the extra equation that this intermediate hinge add to your structure. And this equation is the sum of the moment at this intermediate hinge is equal to 0. And sometimes it gets a little tricky if we did it that way. It doesn't have to be like this. Sometimes I can write it like this. That means that 2 structures are connected to this. So some structure you are gonna find them like this or like this. They are the same thing. This one and this one. By the way, this is just a mathematical representation. This is not how the structure looks like in real life. In real life, if this connection is fixed, this is like this, without intermediate hinge, usually it's something like this, like concrete like this, and the steel is going both ways. That means that this is really, really rigid connection. But if it's something like this, that is this one. This one is something like this. You have a column and this column, and this one is resting on it like this. So this is the hinge, allows the rotation. But this one, the concrete is here, and you have this reinforcement is connecting this all together as a fixed connection. So S is equal to 1. But what if I have members like this? If you have 3 members connecting in one intermediate hinge, it's going to give you S equal to 2. How did I know? Usually S is equal to n minus 1. The number of members going inside the intermediate hinge minus 1. Same thing like this one. This one only gives you one equation, however 2 members are connected because these 2 equations are redundant. It's going to give you exactly the same equation at the end. Okay? So, however, I can make it tricky for you. I can make something, let's say, I have something like this, and this one. You will tell me, by the way, this one is the same like this one. No, it's not the same. It's not about the number of members, it's about the number of structures that this intermediate hinge connect together. This intermediate hinge connect this structure with one single structure, 2 structures together. So the moment right, the intermediate hinge is equal to 0, and the moment that comes from these 2 members together are equal to 0. However, there is a moment in between these 2 because this is a rigid connection between them. Okay, so S here is equal to 2 structures minus 1, n minus 1 is going to be equal to 1. Add one more equation. Let's make it more complicated. If I have 4 members coming to the intermediate hinge, how many equations this is going to give me? 3. S equal to n minus 1. I have 4 members minus 1 is going to give me 3, right? But let's say this. I have a structure like this connecting with an intermediate hinge with another structure here. Something like this. 1. S is going to be equal to n minus 1. I have one structure and one structure, and so it's two structures, so it's gonna be 2 minus 1 equal to 1. So be careful with this, because this one, put it with this. It is something like this and this. These are very rigid connections. So this can move alone and this can move alone, but this one cannot leave this one, and this one cannot leave this one. However, this one, they are all connected to the intermediate hinge. Everyone is free to do a movement on his own. So that gives you an equation, that gives you an equation, that's give you an equation, that's give you an equation, minus 1, all right? So do you guys understand the difference? All right, so right now we understand what the intermediate hinge do and how many equations that we can add to the structure analysis problem. Okay. Now let's see how we can use equations to calculate the static indeterminacy. We have different structures. Each structure has different things. There is something called plane truss, and there is 3D truss, or space truss. There is plane frame, and there is number 4, space frame. And also there is a structure, it's called grids. We're going to talk about the grids in a little bit. Okay, the equation for the truss is equal to the degree of indeterminacy. We call the degree of indeterminacy D, but sometimes because we're going to, there's something called, it's called statically indeterminate, and there's something called kinematically indeterminate. So we're going to distinguish between them. The static indeterminacy, we call it IS. All right? So D is going to be IS right now. So the degree I of a static indeterminacy is equal to, for the space truss, the number of members plus the number of reactions minus 2 multiplied by the number of joints. Okay? We're going to have an example right now. Why is this? Where does this equation come from? If you have a truss like this, once you solve it, you say, oh, that's a statically determinate structure. I was like, how did you know? You'll tell me, oh, I have 3 reactions and 3 unknowns for the whole structure, sum of fx, sum of fy, sum of the moment. However, when we do trusses, to determine the degree of indeterminacy, we don't do it that way. Let's see where the unknowns come from. The unknowns come from the reactions and the support, we don't know them. And every member in the truss has an unknown. This unknown is the normal force inside the truss. So here is the normal force inside the truss. R is the reactions. Okay, we know this. Each joint provides the equation. By the way, this is the unknowns, and this is the equation. The unknowns, every truss, I don't know what is the normal force, and also I don't know what is the reactions. Each joint has 2 equations. These equations are the sum of fx, sum of fy. Like actually when you solve a truss for a static analysis, you take each joint and you make a static equation at this joint, and you say summation of the forces in the x and summation of the forces in the y equals 0, so that you can get the normal force in each member of these. Same thing, you do it here. Same thing, you do it here. So each joint gives you 2 equations. And at each member there's 1 unknown. So that's for the plane truss. How about space truss? Space truss is a little bit different. IS is equal to, still each member has 1 unknown, which is the normal force, plus the reaction. However, the joints has 3 equations. When you deal with the space, you have 3 equations. You have the summation of the force in the x, summation of the force in y, summation of the force in z, because right now you are in a 3D, and still the unknown is the normal force. Let's get to the frame. The frame is way different than the truss. Why? Because each member has 3 unknowns, plus the reaction, plus something called springs. If you have a spring, the spring has an unknown inside it. The normal force inside the spring, if it's a linear spring, or if it's a rotational spring, the moment inside the spring, minus 3 multiplied by the joints plus something called S that we explained right now. Let's take it step by step. Why we, right now in the truss, we only said M multiplied by 1, but in the frame we said M multiplied by 3. Because the frame, any frame, when you cut any 2D frame, when you cut inside the frame or inside the V, there's 3 internal forces: normal, shear, and moment. So this is the unknowns. Normal, shear, and moment. This is the rotational springs or linear springs. Depends on how many springs you have in your problem. The joints, at the joints, it's the summation of the forces in X, summation of the forces in Y, and also summation of the moment. That's what we do when we solve any frame. That's the 3 static equation that we use. And then we said, if you have an intermediate hinge, that adds more equation to your problem, right? So this is the number of equation come from intermediate hinge. It's n minus 1. Okay, for a space frame IS is equal to, each member is going to have 6 unknowns plus the reactions plus the RS minus 6 multiplied by the joints plus S. Why right now it's 6? Because when you have a 3D member in the space, the shear right now is not in 1D. You have shear in X and shear in Y. And moment around X, moment around Y, moment around Z, which is the torsion. Right? And you have the normal force. So you have, when you cut in 3D, there's 3 forces and 3 moments. So you have normal, you have 2 shear, QX and QY, and you have 3 moment, MX, MY, MC. Something like this, like let's say I have a cross section like that. This cross section is going to be something like this. You're going to have, in the 3D, you're going to have normal force, you're going to have shear QX, and you're going to have shear QY, and you're going to have a moment around each one of these sections. That is the internal forces when you work with 3D. But when you work with 2D, there's no way that the other 3 forces are going to drain, because all the forces are inside the plane, like this. What is going to happen if you have forces outside the plane? Okay, all right. So, and the joints provide 6 equations, because you have the sum of Fx, sum of Fy, sum of Fz, and you have the sum of the moment around X, sum of the moment around Y, sum of the moment around Z. That is the equation. For the grid, I'm going to talk about it in a little bit, but the grid has the same equation like the plane frame. It is 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 equal to 3M plus R plus RS minus 3J plus S. And I'm going to talk about the grids in a little bit. Okay, so right now we have the equations that can tell us what is the degree of indeterminacy for structures. Before I start solving problem, I want to explain a concept. It's called externally and internally external and internal indeterminacy. What? External and internal indeterminacy. All right. So I'm gonna write 2 frames. Okay. Let me start with a simple frame. Let's say I'm gonna let me do it with a truss. It's gonna be much more. I don't have this example here, but let's. let's solve these stresses using the same equation that would tell us how we can determine the degree of indeterminacy. If you look at the equation of the truss, it says that IS is equal to the members plus the reactions minus 2 multiplied by joints. By the way, to solve this problem and you get the full point of this problem, you have to do the same way that I'm gonna do. You have to write the equation. You cannot like, oh, I'm gonna substitute in the equation right away. No, you have to write and show me what equations that you are substituting in. So this one has to be written first. And then you will have to tell me what is the count of the members, what is the count of the reactions, what is the count of the joints. You have to tell me all the counts. And if the counts include rotational springs, you have to put RS. Like if there's rotational springs, and if there's S, you have to put all these counts. And count with me. How many members this truss has? The members is count from the joint to the joint. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have 13 members. Reactions, how many reactions do I have?
4.
How many?
4.
4. Because this is hinge, has 2, and this is hinge, has 2. So I have 4. How many joints? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 joints. There is no rotational springs, there is no intermediate hinge. However, in trusses, these things are considered hinges, but when we say hinges, that means in the beam. Because this is already has been taken care of in the equation. Okay? It is not a frame. Alright, so let's say S is out of the equation, and also rotational springs are not in the trusses. Okay, let's substitute in the equation. IS is equal to M plus R minus 2 multiplied by J. So M is 13 plus reactions are 4 minus 2 multiplied by 8. So this is going to give us 17 minus 16 is equal to 1, right? Okay, let's solve the other one. The other one, can you tell me the number of members? It's very easy. It's the same truss except I had the extra member here. So this is going to give me 14, right? However, some of you are going to be confused. Professor, what if I counted this 1, 2, 3, and 4? You can do this if you want. But this only happens if these two members are connected together. Like if your actual real truss is a member and a member, and there's like a screw in between them that connect them together. Okay? But if this is not the case and everyone is moving freely, so that's a member and that's a member. But if they are jointly connected, like this joint is like connecting them, we either move together or go together. But I will assume that this is not the case here.
So screws can be considered as hinges.
Yeah, like if you put a screw that like the thing is, this member is rigid. Like this member is rigid like this. If you try to bend this member, there's a bending moment here. But what I'm saying is that if you put like something, because here, how did you make this connection? You screw them. Like you put a gusset plate, you put something to connect them together. But it allows the moment. Okay? So if you are gonna do the same that you did here, so this becomes 4 members and this becomes joint. But this is not the case here. Every member is connected separately. Okay, so let's say we have M equal 14. So if I did this, I will not count this as a joint. If you count this as a joint, you have to count these as a 4 members, not 2, okay? And at the end of the day, they are gonna give you the same answer. Look at this. If you increase the joint by 1, joint is multiplied by 2. You are gonna increase the members from 2 members to 4 members, so increase the number of members by 2, so they are gonna cancel each other. So it's gonna give you the same answer, but let's do it that way. Okay, members equal to 14, reactions is equal to 3. Joint, we said we're not gonna count this. So if we're not gonna count it, it's gonna be the same like this. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8. So IS is gonna be equal to member plus reactions minus 2 joint. By the way, I write the equation again. Members is equal to 14 plus reactions equal to 3 minus joints is 2 multiplied by 8, 16 is gonna give us 1. So both are statically indeterminate. And what is the degree of indeterminacy? Do you guys remember what is the degree? It is first degree. However, they are different. We call this, look what I'm gonna write. Versed externally and this is called versed internally indeterminate. So we can call it, it's the versed degree indeterminacy, and it's external, and this is internal. So what is the difference? What does it mean by indeterminate? That means there's more unknowns than the equation. If it's externals, that means the unknowns are external in the reactions. So here, this structure is indeterminate if this is a roller. But what happened is that we added more external reaction to make it indeterminate. So this is indeterminately stable. So even, like, to solve this structure, you have to make this as a roller and solve the structure. So we did something external, but the case is this is a hinge. This one, actually, from the outside is determined. I can solve this structure because from the outside it is determined. I have a hinge, I have roller, but if you try to find the internal force, it's going to be really difficult because this one is the extra member that the structure doesn't need to be stable. So if I remove this one from the structure is going to be stable. So the unknowns are internal in the member. I can't find a normal force in this structure. This is the problem. Now let me tell you something. This structure, you cannot get a reaction with the normal way. Some Fx, some Fy is not going to get you anywhere because you have 4 of them. However, if you have the load here, and the load here, and the load here, you can get the reactions here. But if you try to find the internal forces, you might find them here, but when you come here, you're going to stuck. Because you are going to have like more unknowns than the equations. When you try to take some of the Fx here, you have unknown here, and unknown here, unknown here, unknown here. So it's going to be really hard to solve. So that's why we distinguish between externally indeterminate and internally indeterminate. Externally, if the unknowns are in the reactions. Internally, if the unknowns are in the members or are in the springs. Okay? Alright, so let's do the same thing with frames. Like, let's say I have a frame like this, and this frame is fixed, and here there's a roller, and here there's a hinge, and there's loads like this. And I have same frame like this, not same frame, it's different a little bit. Alright, and I'm asking you to find the degree of indeterminacy. Look at the question. Find the degree of indeterminacy of both frames and determine if they are statically, internally or externally. Okay? Okay, let's find out. First, that's a frame, so we need to find the equation of the frame. Can you guys tell me what is the equation of the frame from over there? IS is equal to
M plus R.
No,
No,
3M
plus
R
plus reactions plus R springs minus 3 joints plus S. Okay, that's the equation. Alright, the first thing that it should do, the number of members, number of reactions, number of joints, number of S or RS. Okay, what is the number of members? 1, 2, 3, 4, 5. I have 5 members. Reactions, how many reactions I have? 3 plus 1 plus 2 is going to be equal to 6. How many joints? 6. 1, 2, 3, 4, 5, 6. S. Do I have any intermediate hinges? No. Any springs? Okay. Let's find IS. IS is going to be equal to 3 multiplied by M, 3 by 5, plus 6, 0, minus 3 multiplied by 6, plus 0. So this is going to give me 15. 15 plus 6 is equal to 21, minus 18. So that is 3. So that means there is 3 unknowns. That's a third degree statically indeterminate. Can you guys tell me if this 3 unknowns are external or internal? External, why?
Because
The reactions. The thing is, if I remove this hinge, I remove this roller, this structure is going to hold itself. This fixed actually can take it all, right? So this hinge has a Kissler reaction, and this roller has a Kissler reaction that this structure doesn't need to be stable. So I can see that is 3 externally indeterminate. Alright, so, and we call actually the reactions that the structure doesn't need, we call them the redundants. Like this is redundant reactions. This one, and this one, and this one. The structure doesn't need to be stable. We can take them out and the structure can hold itself. And actually there's many ways that we can make this structure stable. Actually, you can leave this hinge and this roller and remove this face. The structure is going to be stable because these 3 reactions are enough to make this structure stable. So you either, and actually you can convert this fix into hinge. So you release the moment, and maybe I would remove this guy. And this one, I'm going to remove this force, and actually I can make this roller. And right now I'm releasing the X force. So what I did right now, these 3 forces are redundant. I can release the moment from the fixation and convert it to hinge. And if this is called redundant. And I can release this, it's gonna give us reaction, the vertical reaction, and I can release the horizontal here. And these are called the 3 redundant forces. So there is many options that can make your structure, this structure stable. So actually, if the fixation doesn't have like this moment and this hinge that is not there, and I lost the axial resistance of this force, this structure is going to stay stable. So since the unknowns are in the reactions, that means it is externally indeterminate. So I'm going to put them back. I was just showing you the different ways that we can make this structure stable with a bunch of tweaks. Okay, how about this one? Can you guys tell me, before even doing any calculations, is this externally determined or indeterminate? From the external? Determined. Like I can find actually the reactions here. I can find all the reactions here. It's gonna be very easy because it's 3 unknowns from the outside. However, if you try to find the bending moment of this structure, it's gonna be impossible because of these 2 members. When you have a vent, that is gonna make, I'm not sure if you guys solved any vent problems, but I did it like when we designed tanks, culverts for irrigation structures. It's gonna be a lot of work. We have to cut here and we have to cut here because the thing is we cannot solve closed structure. We have to cut in them and show the internal forces and deal with them as external forces. Okay? So it's good that you guys caught that is externally determined. So, but let's find actually if this structure is really determined or indeterminate. How many members do I have?
7.
Okay, 7. How many reactions?
3.
How many joints? 6. S is equal to 0, Rs is equal to 0. Alright, let's solve using the equation. Is is equal to 3m plus reactions minus, I'm not going to put the Rs, minus the 3 multiplied by the joints. 3 multiplied by 7 plus reactions 3 minus 3 multiplied by 6, 21, 24, minus 18, oh. That is, it's gonna have 6, okay, good. Alright, so can you guys tell me if this 6 are internal or external indeterminate? Definitely we agree that this is not external because the reactions outside is 3 and this is the minimum reactions that the structure need to be stable, right? Okay, so definitely these 6 are internal. How they are internal? Because you have 2 members that this structure doesn't need to be stable. These 2 members. Any closed event, you have to open them so that the structure can be solved. So, and why they are 6? They are 6 because this member has 3 unknowns. These unknowns are the normal force, the shear, and moment. And this member has 3 unknowns, are the normal force, shear, and moment. And the thing is, when I solve this structure, I have to open the vents and show the internal forces. Like I have to open this vent and show that this vent has shear, has normal, and has moment. And the same thing has shear, normal, and moment. Same thing here. Shear, normal, and moment. Shear, normal, and moment. And they are equal to each other and they are open in opposite direction. Okay? So right now we have 3 unknowns here, normal, shear, and moment, and normal and shear moment. Once you build your all equations, summation f(x), summation f(y), you have to include this with u. However, when I do them using the regular static analysis, they're gonna cancel each other. Because the thing is, you have the n goes up here and n goes down here. They don't show up. But when we solve with other methods, they are gonna show up. Okay. All right. So right now we know that these 6 are internally indeterminate because they are in the member themselves. Some structures can have both internally and externally. Like if I made this hinge, how much IS is gonna be? Intuitively, like without any calculations. If I made this hinge, I increase the unknowns by 1, so this 6 is gonna be 7, and it's gonna be 6 internally and 1 externally, right? All right, so that's for this. Yeah, was talking about this, I have another equation for you. You might use it, you might neglect it. When we have closed structures, like vent structures, and usually this, I only saw the application of this structures in the irrigation structures. I'm not sure if you guys know the culverts. Have you heard about the culverts? The culverts is like a reinforced concrete section that is closed. And the way that we solve it, we take one strip, 1 meter, and we deal with it as a frame. And when we solve the reinforcement, we get the reinforcement by every 1 meter. So when we find the reinforcement in 1 meter strip, we distribute it with the whole culvert. So that shows up in the culvert. The thing is, there's another equation when you have closed vents. This equation it says that 3 multiplied by the number of vents plus the reactions minus 3 plus S. It's gonna give you the same answer like this one. Like if we substitute here, I have vent here and vent here. So I have 2 vents, this one and this one. So 2 multiplied by 3 plus the reactions is 3 minus 3 plus S, 0. So this is gonna give you 9. 9 minus 3 is equal to 6. That's a simplified form when you have closed vents.
I have another question. You mentioned that we can make it determinate by removing the 2 bottom elements, but if we remove the one in the middle, the vertical one, it's still a stable structure, right?
It's a stable, but it's gonna stay indeterminate because you only removed 1 member, so it turns out to be 1 vent, right?
No, I mean if you remove the 2 in the bottom and the one in the middle as well.
Yeah, but the thing is, you only need to remove the 2 in the bottoms to make it open structure. However, actually, you can any member you are going to remove, you have to show the internal forces. Like let's say I can solve this in a different way. I can keep this one closed, and I can open this one. Once the whole structure is open, that's an open structure. So that is going to solve your problem. So you only need to cut in 2 members and show them. But the thing is, what he told me, I'm going to cut in the 3 of them. If you cut in the 3 of them, this part is going to be unstable, it's going to be free. So once you cut, you have to cut your structure in a way that can make it still stable. Okay? So that when I cut in 2 members, and that's all what I need, this structure is still stable. No elements are free. Okay? So that's what I did. Here's a cut and here's a cut. That's one way to do it. Or you cut here, and this one is holding these 2 pieces. Alright. By the way, you can solve it by cutting any problem, even like, I don't know. But the thing is, you have to show the internal forces. Okay? Alright, so with this, let's solve some other problems. We have like 8 minutes. this structure and find the degree of static indeterminacy and determine if it's externally or internal. This is spring, so we're gonna stay in the same equation. IS is equal to 3 members plus reactions plus springs minus 3 joints plus S. Okay, let's find the number of members here. Can you guys tell me? By the way, this is not a member. This is a spring. You can count it as a spring. You don't calculate it as a member. If you are gonna calculate it as a member, you can, but you have to calculate 2 joints, start and end. Okay? Alright. Anything you are gonna calculate as a member, the start is gonna be a joint and the end is gonna be a joint. Alright? Okay. So I'm not gonna count this as a member. I'm gonna say that this is a spring that has one unknown and this is a spring that has one unknown. So the total number of members are 4. 1, 2, 3, and 4. Okay, how many reactions do I have?
8.
I have 3 here, and this is hinge, and the hinge has a rotational spring on top of it. If you are gonna calculate these springs as reactions, you cannot include them as a rotational springs here. So you can include them in R, or you can separate them, but you cannot double count them. Okay? So the thing is, this joint is the same like this joint, but the difference is this is a stiff, rigid fixation, but this is a flexible fixation when the soil allows a little bit of moment. Okay? This is gonna take us to the concept of rigid, flexible, and semi-rigid. Okay? Sometimes when you have the soil is loose and doesn't allow the rotation to be free, and at the same time doesn't resist the whole rotation, it's something in between. We put it like this way, okay? All right.
So how many reactions does that one?
That one has, this one has 2 because it's a hinge. So I have 2 here and 3 here, so this is gonna give us 5. And how many springs do I have? 2, because I have 1 rotational, 1 linear. And okay, the tricky part is, this is not tricky, the joints. 1, 2, 3, 4, 5. Okay, I only have 5 joints. What is tricky about it? Some of you are gonna count this as a 2 joint. This one and this one. This is not 2 joints. This is only 1 joint, but I separated them to show you that there is an intermediate hinge between them. Because usually it is something like, as I showed you before, something like this. So they are separated. But it's only 1 joint because there is no member in between them. Okay? Alright. However, if you want to do it like this, and you say, oh, I have something like this, and I'm going to count this as a member, you have to count this as a joint, and this is a joint. Okay? So the easy way to do it is the same way that I was doing. This is going to count it as a 1 joint. So I have 1, 2, 3, 4, and 5. And if you are going to count this as a 6, this is going to be added as a member. Okay, so I have 5 joints. All right, how many S do I have? That's the tricky part.
Should be 0, no?
How 0? I have 2 intermediate hinges.
That's 1.
This one is an intermediate hinge, and this one is an intermediate hinge. So if you guys remember, when we're doing S, if I have something like this, 2 structures is connected, it's going to give you S is equal to n minus 1. So 1, 2. So n minus 1 is 2 minus 1. This is going to give us 1 equation. And this is going to give us another equation. So S is equal to 2. Alright? Okay, so let's substitute in this equation. So I'm going to have 3 multiplied by 4 plus reactions is 5 plus RS is 2 minus 3 joints, 3 multiplied by 5 plus 2, and this is going to be 12, 17, 19 minus 17 is going to be equal to 2. But can you tell me if these 2 are externally or internal? The thing is, I don't have any closed vents. If I don't have any closed vents, so that means there is no internal. This is an open structure and this is an open structure. So there is no extra members for this structure. When this is going to happen, if I have a member here. If I have a member here, yeah, I have closed vents. And by the way, it's not fully closed. Why? Because they have intermediate hinges here. talk to you maybe a little bit about the difference between if you have a vent like this and a vent like this in a little bit, like if you have an intermediate hinge here, okay? All right, so there's no any closed vents, so definitely it's in the reactions. So let's count. Let's say
Is it because of the springs?
you can remove the springs. Like if I remove this spring, it's gonna be stable, and this one is gonna be stable. There's different ways to make it stable. But let's say for now, this is second externally indeterminate. All right. So let's see what is the different options that I can do for this structure to be stable. By the way, what we are gonna do right now, we are gonna try to find what are the redundant reactions that the structure doesn't need to be stable. Let's say if I remove this spring, is the structure gonna fail? No. Why? Because this is still beholded by this part. So this reaction can be a redundant reaction in the spring. If I remove this rotational spring, and this structure is like this, I see that this structure is still stable. Yeah, you will tell me if my structure is something like this, that's unstable, right? Because this structure, once you put load, is gonna flip. But there's a beam is connected to the other one holding it from here, so that makes it stable. So I can say that the moment in this spring or this spring, the structure doesn't need to be stable. So I found the two redundant reactions that the structure doesn't need to be stable. However, there is a lot of options that you can do for this structure to be
Can
stable.
you keep this spring and make that a roller too?
This one, maybe, but the thing is you have to find out. Okay, like if I made, let's say,
Technically, yes, because of
the spring is gonna make it something. If you mean like if I make this
roller.
like
Keep this rotational spring.
this, so let's look what's gonna happen. And I have this one is resisting the moment. So basically,
No, because of the force in the X is gonna slide.
let's say if I put a load here,
You could just add like
I
another
think this
roller.
one can resist it as a moment.
But the thing is,
Underneath
it's gonna move right? Because the hinges are gonna fold down.
Yeah, this one is gonna allow this one to move that way. But what I'm saying, let's say that this is not. The thing is, we can represent it by something like this. This is called guided connection. Okay, so we're gonna take this support. The thing is, if you push that one that way, this one is gonna slide. It's gonna be unstable, especially if that is not fully fixed. This guided support only we use it if this is a fixation. Like if your support is not like this, it's something like this. So what you are saying here, what if we made this release the horizontal and become like this? So the only reactions, if my support is like this, I'm gonna have this and this, only vertical and moment, and I release the X force. So once you put a force that way, this one is gonna go that way. But if this connection is fixed, it's not, it's gonna be okay. So the thing is, when you try to find the redundant force should be a forces that the structure doesn't need to be stable. So try to find a better one. Okay, let's put this back. I'm gonna put it as a hinge, and we found out that the external is something like that. If somebody's like, oh, I have, maybe it's internal. What if I cut here? If you cut here, this one is unstable. Once you cut in this section, this one is gonna fold on itself. Okay? All right, so we solved this structure. By the way, let's talk about this part before I delete it. Like, okay, if this is the vent, you need to open in this vent like this to show the internal forces. And you're gonna have a moment here and a moment here. So you have three unknowns in this vent. Three unknowns. However, this vent only has two unknowns. Why? Because there is no moment. The moment here is equal to 0. So you only have shear and normal. And the moment left and right is equal to 0 because of the intermediate hinge. So it's not fully closed vent. That's my thing of it. Okay, let's find about this one. Okay, that's still a frame. Can you guys tell me what is the total number of members?
Are the ones in the middle connected?
Yeah, it's connected here.
10.
10. How about the joints?
9.
9. How about the reactions?
9.
9. How about rotational springs? Only have one. How about S? It's a little bit tricky. Look, this hinge doesn't, like, it's not in between these two membranes. It is just
3 of
something like this. Connecting how many structures?
2.
2. So S is equal to 2 minus 1 is equal to 1. It only add one external, one construct equation. Okay, so I have all what I need to calculate I is 3m plus reactions plus rotational springs. These all the sources of unknowns. Every member has 3 unknowns: normal, shear, moment. Every reaction is unknown. Every spring has an unknown, either a force or a moment. Minus all the sources of equations. Each joint has 3 equations plus each group intermediate hinge provide an equation. Okay, let's calculate this. 3m is going to be 3 multiplied by 10. Reactions is 9. Rotational springs is 1. Minus. Joints are 9 plus S is 1. Okay, I have 30, 39, 40. 40 minus 28 is going to be 12. I have 12 unknowns. Okay, let's find out, are they externally or internally or both? What do you guys think? Why is both? That's a really good guess. So the thing is, this is structural. If I remove these two fixations, it's gonna still hold itself. Because this fixation actually is like a tree. If you have a tree, it's fixed in the ground, and there's a lot of branches that's coming out there, like branch, 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 and all these are branches. So definitely, it has 6 externally indeterminate. So this 12, 6 of them are external. How many internal? Definitely 6, but where are these 6? Can you tell me?
And the reaction?
I have closed vents, right? The thing is, this is another vent and this is not a vent. Okay? Alright, I only have these 2 vents, and definitely it's inside these vents. I have to open them. You either can open this one and open this one. It's gonna give you shear moment and normal shear moment, and this one is gonna give you shear and normal shear moment. Okay, that's one way to do it. And also there is multiple ways. You'll tell me, how about this part?
Oh yeah, that wouldn't hold itself.
No, it's gonna hold itself. The thing is, you can treat this part as like a fixation, like the same one. This one and this one are like each other. This one is stable on its own, and this one is stable on its own. However, this one is not as rigid as this one. So this connection actually is like this connection. There is a shear, there is a normal, there is a moment. You'll tell me, but we release the moment by putting this intermediate hinge. I release the moment, but I put another spring to bring the moment back. Maybe it is not fully rigid, but it is semi-rigid and can take moment. Like if you cut here, this is still stable. When it's gonna become unstable, once you remove this rotational spring, it's gonna be unstable. Because the thing is, it's something like this, as an intermediate hinge. But once you put the spring, that means like, it can hold itself a little bit, okay? So the spring is still can make it stable. So I still can cut here and cut here and do it. Okay, that's one way to do it. So we showed if we cut here and cut here, that's one way. We cut here and cut here, that's also one way. Also, you can do this. You cannot cut here. You can keep this, and you can open here. Once you open here, you show 2 forces. You show the normal and shear here, and you are cutting in this spring, and you have to find the moment inside the spring. So that's also one way to do it. Okay? All right? Okay, but once we do this,
You cut at the top.
you can cut at the top. Like you can keep this, and you cut from here and cut from here. The whole point is then to open the vent. That's the whole point of the structure analysis. The thing is, our problem is like when we do the static, and actually this is similar concept to the trusses. If you guys remember when you guys solved the trusses, I'm not sure, maybe a long time ago in the static, the thing is to solve it, you have to cut and show the normal force in each member, like this, and you take this out, and then try to find the summation of the force X and Y. It's the same concept over there, but you guys never saw a closed vent frame. All the trusses are closed vents. That's why when we solving them, we have to cut in each one to solve each joint by itself. That's what we used to do in trusses. Frames is the same way, but the thing is, trusses was easy because it's only one normal force inside each member. Here, it's much more difficult because once you cut in each member, there's three forces: normal, shear, and moment. Okay, so that's for now. We covered most of the stuff related to static indeterminacy. Next time we're going to solve two examples of this and start a new topic. It's called kinematic indeterminacy. And I'm gonna upload, I uploaded the first lecture on YouTube. I'm gonna put it on Canvas today. I'm gonna upload last lecture notes and this lecture notes on Canvas. And we are gonna have our first quiz on this concept by Thursday next week. Okay, so 1 week from now. All right, see you guys next week.
Thank you.